Hello and welcome to the Terran Space Academy, where we help prepare you for a bright future in the space industry. Please don't forget to stay connected, let us know what you like, and help us out on Patreon if you can, so we can keep bringing you great lessons on space science. Today I want to draw your attention to two very different subjects. One is the amazing progress of Sierra Space. We have a comprehensive lesson on this company here, and I'll add a link to it at the end of the video. But today, I want to draw your attention to two significant innovations brought to the space industry by this company. The first is the Dream Chaser spacecraft. Originally designed for crew, it was repurposed for cargo only, when it was passed over for crew capsule development, in favor of the SpaceX Dragon and the Boeing Starliner. NASA ended up giving Boeing almost twice as much money to develop the Starliner as it gave to SpaceX for the Dragon. $4.49 billion taxpayer dollars for Boeing versus $2.6 billion for SpaceX. I'm not sure what the logic there was, but Boeing has once again failed miserably. Taking engineers out of the top management loop has essentially destroyed this company. If that money had been given instead to Sierra Space, I firmly believe that America would have two operational crewed spacecraft right now. It is never a good idea to give in to the sunk cost fallacy, or to have no competition. And despite governmental short-sightedness, the Sierra Space Dream Chaser should fly soon. Sierra Space also successfully pressure-tested their full-sized habitat called LIFE, which stands for Large Integrated Flexible Environment. The world may soon have an inflatable commercial space habitat, potentially much larger and more efficient than the ISS. We could have had this decades ago, if politics had not shut out the Bigelow Corporation's products. The United States government has spent the last half-century sacrificing innovations in space systems technology to political favorites, payoffs, and politician kickbacks. Allowing the contracting companies to donate directly to the politicians who gave them billions was one of the dumbest things the American Supreme Court has ever done. Every industry needs healthy competition. And as we celebrate the amazing success that SpaceX has brought to the space industry, we cannot fall victim to playing favorites ourselves, or we endanger all of our success by ignoring the merits of the competition. I have been highly critical of the United Launch Alliance, but I applaud the success of Vulcan and have high hopes for New Glenn. I also look forward to seeing Dream Chaser soar to orbit on the Vulcan rocket system. But I'll be even happier when it can carry passengers. Of all these designs, Dream Chaser will be the best lifeboat available. That's because all of these capsules are one failed parachute release away from catastrophe, while the Dream Chaser can glide to a safe landing without one. Lifeboats will be a major concern as humanity starts moving to orbital habitats. And that brings me to the second point. Whenever I acknowledge the success of China's space endeavors, like their space stations, crewed spacecraft, and other innovations, I get accused of being a propagandist for the Chinese Communist Party. I don't know how many times I've heard that China is copying Soviet and American designs. My response is, of course they are. We did too. At the start of the space race, the Soviets sent a satellite to tour America. In a scenario worthy of a Mission Impossible movie, American spies were able to sneak past the guards, disassemble and photograph the satellite, and put it back together by morning. That doesn't mean I'm saying it's okay for China to steal American technology. I'm just saying we've done it too and should expect it. We must also separate the success of China's scientists and engineers from the government of China itself. Engineers and scientists don't choose the country they grow up in, and quite often have very different opinions on how things should be run. In fact, almost all of my favorite rocket scientists have spent some time in prison or exile. Korolev and Glushko for not renouncing targeted colleagues, and von Braun for complaining about slave labor conditions. While I applaud the brilliance and success of China's space scientists, I'm still hoping with all my heart that the US, Europe, and other democratic nations will control access to space. If China gets to the lunar South Pole first, all they have to do is use an automated rover to 3D print a small wall around the best ice reserves, put in some habitats, and declare it the border of their base. By international law, no one can come within 500 meters without permission. Add a few magnetic rail launchers for orbital resupply, and a few big lasers, for micrometeorite protection, of course, and they would be able to keep anything from staying in orbit around the Earth, much less reach the moon. I have heard talk that the US government is considering canceling both Starship and the SLS in favor of something like the shutdown Constellation program of the early 2000s. While I have pointed out ways to go non-reusable and get an outpost to the moon faster, I am not in favor of another walk around and leave scenario. The world needs several permanent growing colonies on the moon. I think that if the US government doesn't start funding more innovative startups and stop underestimating the competition, we will need to speak Mandarin to get permission to go to orbit. Let me know what you think, and stay safe. At Astra Pro Terra.
Attention all operators on countdown 1. This is the final go, no go for flight 2 of Starship. Again, our T0 is at 7 a.m. Central. Raptor 1.
Go.
Raptor 2.
Go.
Stage 1.
Go.
Stage 2.
Go.
Copy, go for flight. Clock is rolling. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. We have liftoff.
Boost ratchet cut off. Stage separation.
We were just here at Marshall Space Flight Center just about 100 days ago doing our most recent subscale burst test. That one had a blanking plate integrated into it, and on this one now we have 2 blanking plates integrated.
Our team has moved incredibly quickly to iterate on this design. Now we're able to put habitats in space. For example, life will achieve 1/3 of the volume of the ISS in one launch, where that previously took 10 to 15 launches to achieve that same volume.
And we believe that having the ability to build space stations together with our space transportation systems and bring those together into an ecosystem allows us to find things that we can't discover on Earth. We think about creating an end-to-end solution that will enable the orbital age. We think about every industrial revolution that's come before us has really positioned us for now, for this new age.
Soft goods have a previous track record in low Earth orbit, actually. They had put up a inflatable airlock. Following that, there was 2 prototype modules called Genesis 1 and Genesis 2. Shortly after that, the Bigelow expandable activities module. So we're trying to continue that trend with Sierra Space.
The ability for Sierra Space and ILC Dover to place a blanking plate inside this soft goods shell is the next generation technology. Those blanking plates aren't just for windows. We can place on there antennas, we can put another airlock on there, we can have radiators, solar arrays, robotics. We are going to demonstrate to the world that Sierra Space is the leader in soft goods habitation.
The full-scale unit behind me here is really comprised of 2 main components. We have our metallic ground support equipment and then the soft goods. The core is 18 foot tall and the diameter is 27 feet. And we do what we refer to as sleeving. and that sleeving is where you basically drop the soft goods over the top of the core. Today feels a lot like the culmination of all the subscale tests that we've done, really leading to this full-scale test.
So our ultimate burst pressure test day is really about two things. One, it's about verifying the success that we had on our subscale test efforts. So we far exceeded the NASA safety and certification requirements with those subscale tests. And so now it's really about extrapolating those to this full-scale test and verifying that those results are repeatable.
We have learned a lot in terms of how to architect the material, how to weave the material, how to build the material, at the different layers of the material, how to think about all of that so that when we actually get it in space, it's harder than steel, has much more in terms of durability, and the greatest invention is windows in soft good structures.
The teams have worked extremely closely, not just to engineer something as unique as what you see behind us, but we continually learn how to mass produce so that as this becomes more and more of a viable technology, we can be first to market and make sure that we can deploy this type of technology across multiple applications.
It's the technology that's represented behind us that's going to allow us for the first time not just to think about what to put in space, we can now think about what we're going to produce in space to benefit life on Earth.
Between Blue Origin and Sierra Space, we have got some of the best people in the industry. So I'm excited to see the life habitat make it to space, make it to orbital reef, and just the capability of having such a large habitat in space enables living in space in a way that we've never been able to before.
The whole idea is that we're gonna grab our inflatable life and just take it to the max, see what kind of PSI we're gonna get to. We're hoping that it is somewhere in the 60 PSI.
Bursting is so important because the data we achieve from this burst test and subsequent burst tests will allow us to refine our design for Life 1.0, 2.0, 3.0, and beyond.
Okay, you guys clear? 45 PSI, 50 PSI, 50 PSI, 55 PSI, 55 PSI, 65 PSI. On the way to burst, go Sierra Space, go NASA. Starting to go down in pressure. So maybe it's a leak from the test article and it's trying to overcome it. We're dropping just as fast as we were filling it.
We didn't burst. There was a little bit of an issue that we're taking a look at. There's some type of leak rate or leak that's happening in the article. We're gonna go out there and do a post-mortem review.
It looks like there was a valve failure on our 6-inch vent valve.
So good news. The article could still be tested, and we're gonna go down and close those valves, fix it. Beth and the team, along with NASA, will come up with a mitigation process, and we'll move forward.
We had a really successful test. Although we did not burst our article, we did surpass the factor of safety threshold recommended by NASA. Today we're going to be back in the control room for part 2 of the test. While we did surpass our threshold yesterday, we still want to burst our test article to really see how much margin we have.
Ready to burst, go Sierra Space, go Odyssey, Dover, go NASA. 55 PSI, 55 PSI, 63 PSI, 63 PSI. 70 PSI, 70 PSI.
Here comes my number.
75 PSI, 75 PSI. That's insane.
We're not a company that's trying to escape Earth. We're not a company that thinks that we ought to leave the planet. We're a company that's committed to this home and making it better. Ultimately, our focus is to benefit 8 billion people. We believe we will help find cures to the world's hardest problem, find cures to leukemia and other kinds of cancers. Think about longevity in ways we can never have thought about. Next generation of energy, next generation of computing power. It will change everything.
We were just here at Marshall Space Flight Center just about 100 days ago doing our most recent subscale burst test.
We don't even know if it's going to work.
You don't get a second chance once it's launched. Further and further you go with each thruster, each test, there's a new problem that arises.
Building rockets is just so much fun. Everyone talks about, well, it's not rocket science. Well, for me every day, it actually is rocket science.
There's something about just taking fuel and turning it directly into energy that really can't be beat.
I like things that are loud and fast and exciting, and rockets are all those things.
This is the time to follow your dreams. Make your way up to the top. Take a breath and make it out of here.
Who wouldn't want to say that they go to work every day and work on rocket engines?
At its core, rocket engines are quite literally the driving force behind space exploration. They're the one source of transportation that we have that is so energy dense that you can pack enough oomph into it to get into space.
We have rocket engines that are designed and developed and built in the United States. With those engines, we're going to be the leader to move forward and move farther into space.
On the frontier of a natural preserve in Wisconsin, the Sierra Space team embarks on a mission at the Badger Propulsion Test Facility, building and testing their own rocket engines.
We have 28 acres as our operational area. We have 4 test cells and 5 test stands, and that's what we use for our propulsion testing here.
This is the fuel bay of Test Cell 3. These are hydrogen run tanks. They are 750 gallons each. They're vacuum jacketed. We can pressurize the system up to 6,000 PSI, and that's what we use to push hydrogen into the engine. The biggest engine we're testing is 35,000 pounds, and we can go up to 150,000 pounds on this test stand.
Dream Chaser uses a specialized reaction control system to maneuver once in orbit. Known as RCS thrusters, the Dream Chaser will have 26 installed throughout its hull to help guide America's spaceplane into the orbital age.
Working on my undergraduate degree, I had a professor that looked at the class and he said, as engineers, you are in a position to change the world.
Engineers, machinists, and technicians work together, intricately planning and tooling every detailed application.
I get to put my hands on spaceflight hardware every single day. It's figuring out how the heck we're actually going to put this thing together.
Seeing the theoretical things happen in the physical world. That's the coolest thing up here, because until something shows up here and gets tested, it's all theoretical. You don't even know if it's going to work.
You don't get a second chance once it's launched. Further and further you go with each thruster, each test, there's a new problem that arises. It requires some really scrappy ingenuity a lot of times. I consider myself more of a rocket surgeon than a rocket scientist. So.
Making something to such a high degree of precision that can get strapped on top of a rocket and launched into orbit, zooming around at thousands of miles an hour. It has to be rigorously tested and able to go into space reliably and have people depend on it for their lives.
With Dream Chasers designed for multiple missions, the team pushes materials to their limit, knowing that once in orbit, the RCS thrusters are the only driving force behind the spaceplane.
The main project that I've been working with for the last year and a half has been the reactive control system, which is the thrusters on the nose and the tail and the front. I'm working on a monolithic nozzle right now that helps with re-entry, and it helps with course corrections and stuff like that for docking with the space station. So in order to get this, it starts out like this. Rare earth metal, niobium, extremely expensive. Certainly don't want to waste any. Trying to get tools in all these short little areas and crevices was not an easy task. From start to finish, just for the machine time, was 24 hours.
We're working on the interface between our combustion chamber and the nozzle itself. Due to the amount of pressure in here and the extreme temperatures it faces, it's quite the engineering task. They use the vortex propulsion system. It takes the hot gases, and instead of just directly expelling it out the back of the thruster, it causes it to spin. And when you spin those gases, you can concentrate the hottest part of that reaction right down the middle, so you can actually use the burning gases to keep the thruster itself from melting.
Using the vortex technology for cooling, Sierra Space has been able to develop a revolutionary 3-phase RCS thruster. advancing technology, not just for Dream Chaser, but propulsion for a wide range of other applications.
The thruster itself is a 3-mode thruster. It can fire in low, medium, and high thrust modes. The low and medium thrust are monopropellant, high test per oxide. We can get 40 pounds for low, 60 pounds for medium thrust. For high thrust, we do an injection of RP1, and that gets us up to about 110 pounds of thrust. We're well above the 90% efficiency range for overall combustion efficiency. We can use fairly small mass flow rates to get the thrust levels that we're at. 110 pounds doesn't sound like much, but on a 14-pound thruster that's completely pressure-fed, that's pretty great.
It's probably the most advanced RCS thruster that's ever been developed. These systems are a huge achievement. We're building something here that has never been developed before. We're doing everything we can to make sure that we put a vehicle in orbit that one day will revolutionize low Earth orbit.
At Sierra Space, proof of concept comes as every application goes through rigorous testing to qualify for the harshness of atmospheric change, unforgiving burn and re-entry temperatures, and the vacuum of space. Each piece gets tested and refined and tested again and again.
We have the bimetallic flange, so one metal here, the nozzle's a completely different metal. We're having a hard time figuring out how to seal between those two metals.
The first thing we're going to do for this test today is make a new gasket that's going to seal between the catalyst bed and the actual thruster core itself. We'll button up the bell jar, set all pressures and regulators, and then head out low peroxide and get going. So this is the test cell that we test the Dream Chaser RCS thrusters in. The ability to test the thruster in space-like conditions is a real challenge. Actually being able to maintain vacuum and heat at the same time. So we had to find a way to cool the hot gas so it didn't interfere with the structural capability of the vacuum chamber itself. A lot of these parts would melt and burn through in about 10 seconds or less. So we had to water jacket and spray in water into the vacuum system, which was upwards of 2,000 degrees.
We'll send all that data down to the design team, and they'll pick the final design for the engine that's going to go on Dream Chaser.
To me, Sierra Space is leading the charge into the orbital age.
We are pushing the edge of technology.
All the effort that we put in here, all the time and blood, sweat, and tears that we're pouring into this, it really makes it worth it.
After years of research and meticulous testing, the RCS thrusters are approved to go through production and get installed on Tenacity.
Knowing that the hardware that I'm helping build and test will be going into space is so incredible and so rewarding.
The Badger team hands off final designs, knowing their work is destined for space, playing a pivotal role in guiding Dream Chaser's journey to the International Space Station and beyond.
It is just amazing to work on a vehicle like this because we're doing something that's never been tried before. We're truly reaching into the future, and it means a lot to the pages of history as far as the space frontier.
What we're doing here is going to change the commercial landscape in spaceflight. There's no one else doing what we're doing. The Sierra Space platform, it's comprehensive. It's not just a small piece of what's needed for spaceflight. It's the whole thing. It's how you get there, it's how you stay there, it's how you come back, and it is going to pave the way for how Earth interacts with space. And that's something no one else is doing. There's many pieces of the puzzle out there, but Sierra Space has the entire puzzle. So it's really awesome to be able to make that kind of an impact, not just on Sierra Space, but the world.